So again, we are back with the examples of force displacement method using matrix. So today I'm going to do another example using a two-span beam, right? So if you see this beam, right, first thing is, so you get confused, okay, what is this? So this part is large and this part is small, right? But you don't need to, right? You don't need to be afraid because all the things are given, right? So it simply says your I is twice this value, right? That you can substitute during uh, during the math, right? So I'll rotate this as A, B, and C, right? So the first thing is whether to use force method or the displacement method, right? So to use force method, shall we see how many reactions are there? So actually, you have here you have vertical reaction and horizontal reaction is 0, right? Because no horizontal loading. And you have bending moment. And here also you will have a vertical reaction. Here also you will have a vertical reaction. And let's consider this bending moment, right? So altogether you have 1, 2, 3, 4, 5. If you want, you can consider these, okay, right? No problem, right? No problem because there's no horizontal axial loading, right? So that's why I don't need to consider those for now, right? If you have some axial loading, definitely you need to consider that. So you already have 5 unknowns, right? 5 unknowns, and you have 2 equations where the vertical force equilibrium and the bending moment equation. And you can't use the horizontal reaction equations as well. So that means you need to solve for 3 redundants. There are 3 redundants, right? So that means you need 3 additional equation. But what happens displacement? Here, the kinematic display indeterminacy, the unknown displacements are 0, right? Because it's a fixed support. You know the vertical translation is 0, horizontal translation is 0, and the rotation is 0. And 3 displacement, and all of them are 0. That means those are not any longer the unknowns. Those are known values. All things are 0. Here, this is a pin support. So the only possible thing is it can rotate about this axis, right? So we have 1 unknown. Here you have 0 unknowns, right? Here also the same 0 unknown. So that means unknown displacements are 1, right? It's directly 1, and unknown forces are 3. So your statical indeterminacy is larger than kinematic indeterminacy, right? So this is Ki, this is Si, right? So what happens is it's better to use displacement method where you can solve it using less number of steps. So that means you are solving for this unknown displacement, right? So if you are solving for this displacement, first thing you need to do is you need to make it 0 and make your primary structure, right? So you are solving for something, you don't know the value, let's say theta, right? So I'll consider, in next slide I will write it. So how do I make it? So the easiest way is, right, I can, so one more thing, if you want, you can use force method as well, but when using force method, please consider, right, it will be easier for you to use hinge forming. The other method is not going to be easy because this is geometrically not consistent, right? This is E in I. So when you use hinge method, you automatically divide it to two parts and then you can solve it easily because you are considering each span separately. But if you are solving without hinges, it will not be easy, right? So we are working on this as displacement method, so we are fine, right? So I will take the actions to determine as, I'll say this is BA, this is MA, this is VB, this is VC, and this is MC, right? And yes, we will come to that later. So I will consider this bending moment as total bending moment MB. So you know total bending moment at a internal pin or roller is going to be 0, right? Because you know usually that happens with same bending moment, right? In each portion separately, right? So right. So the total bending moment is MP, right? And we have a value of theta, right? So first thing I'm going to do is to make the primary structure. So this is very easy, right? So simple beam. So I'm going to fix this. Only difference is this is EI and this is 2EI, right? So I write it here. I don't need to draw as it is, right? So why did I fix here? The unknown displacement was theta, and I make sure that it is 0 for the primary structure, the loading, right? This is Q. So to simplify easily, I will assume QL is equal to W. Okay. That's going to be easy when you simplify, right? This is L. This is going to be L as well, right? So since these are fixed supports, right? So it's more like individual spans, right? So this is fixed, right? Here. So there will have a reaction of this much. It's going to be QL over 2. This is going to be W over 2, right? This is going to be W over 2, right? So, and here as well. And you know the friction moment, right? So I'll take clockwise positive, right? always clockwise positive, so that means clockwise bending moment. Here actually you have an anti-clockwise, so the sign is negative then, right? Okay, if you draw it in the anti-clockwise direction, it's positive sign, okay? Because you already mentioned the correct sign. Here I'm taking always clockwise. If something is negative, so that means that is anti-clockwise, right? So this is going to be QL squared over 12. This is going to be QL squared over 12. And this is going to be WL over 8. Friction moment. This is going to be, this is negative, okay? Positive WL over 8. Right? Is it okay? So get used to this one, right? So in the displacement method, we use the equilibrium, right? For the equilibrium, we solve, right? So we need the total bending moment. So we consider the total displacement, right? So this theta, right? Theta, and the corresponding bending moment is total bending moment, MB, right? So yes, this is our primary structure, right? So I can write, so there's only first one coordinate, one redundant coordinate. So I don't think you need matrix to solve this one. So for the actions, I will use a different coordinate system, as this is 1, this is 2, this is 3, this is 4, and this is 5. So the first coordinate, right? So I'm going to determine the theta, right? I'm going to solve for theta, but in order to do that, first I make theta 0. Then I can apply it to the system later, right? Without any loading. So with loading, it's going to be complex, right? And yes, so I can take now MB. So for the primary structure, MB is going to be this plus this. So I can take QL is W. So this is going to be WL over 2L minus WL over 8. So that's going to be how much? 24, 2, 3 minus WL over 24. Right. So this is your bending moment. And so next, so your bending moment is okay, right? So that does not depend on EI, right? So still EI did not come to role play, right? So again, you can find the actions here. So actions in the restraint structure. So this is actually MBR, moment B at the restrained position, right? So that's going to be first one is, so I'll put QL as W, right? So that's going to be WL over 2L. This is QL is W, so that's going to be, so an upward positive, okay? W over 2. This is going to be W over 2 plus W over 2, that's going to be W. And this is also W over 2. This is your action matrix, right? Okay, so I now need to apply the displacement which I made 0, right? So since I have loading everything here, I can that apply to the structure without any loading, because I'm going to superimpose everything. I need to add these things, add these primary structure and redundant structure to get the final structure. So it's okay to have W in any of the stage. So fix everything, and with W I take everything, and then I can apply the unit displacement for the structure without any loading, right? So how do I apply that is, I need to apply a unit rotation, right, in the clockwise direction. So this is going to be 1. So theta is 1, okay? Theta is 1. So if you apply like this, so your beam will, so anyway, if it is fixed, so your beam will be perpendicular to the fixed support, right? So you are rotating the fixed support, because you know at the fixed support rotations are 0, right? So only possible rotations is when you rotate the support, right? It's going to be like this. It's going to be like this, right? So this is 1, is 1, right? So I need the bending moment induced at these locations, right? So you know, if you have fixed supports, and if you apply theta, so the bending moment induced in the nearest location is 4 ei theta over L, and this is bending moment induced here is 2 ei theta over L, and both clockwise, right? Both clockwise. So here it's going to be clockwise. It's going to be clockwise. We don't need here, right? We don't need here actually, but for the actions we need, right? We need, it's going to be right. Okay, so if you apply like this, so you can even consider what are the reactions as well. So I can easily take it from the appendix. So here, can you see? So it's the rotation is going, so the bending moment is going to be 4 ei over L, and the far end it's going to be 2 ei over L. Why? Because the carryover factor is half, right? And the reactions, vertical reactions, are going to be 6 ei over L squared, right? And we can make the directions as well. So the easiest way is just consider what this beam is trying to. So this beam is trying to push this position in this way, right? So it needs to keep it back. So the reaction should be in this direction. Compared to this location, right? Compared to this location, right? So it tried to bend this beam in this way. Think about this one, right? Think about this one. So then the reaction should be in this way to keep it back in the position. Compared to this location, this try to move this beam in this way. That means this end will have a reaction like this, right? So compared to this one, this is trying to bend this beam in this way, so it needs a reaction in this way. So these are going to be 6 EI. Now EI come to role play. So this is EI. This is still EI. But this is 2EI. You remember? So that's going to be 12EI. Why I have to substitute 2EI instead of EI, right? So that's going to be 12EI over L squared, right? Twelve EI over L squared, right? So the rotations, I can write. So you remember 4EI over L. So this is 2EI, okay? The beam is original 2EI. So 4EI over L becoming 8EI over L. This is going to be 2EI over L, but the beam is original 2EI. So that's going to be 2 into, so I'll just substitute so that you can see EI over L. So that's going to be 4EI over L. That's how these things came, right? But here, this beam is originally EI. So this is going to be 4EI over L. This is going to be 2EI over L. So your M, bending moment, due to unit rotation. So that means force due to a unit displacement. What did you do? You had a theta deflect rotation at B and you make it 0. Now you add a unit displacement and calculate the force. If your force is unit, if your displacement is unit, this is a unit value 1. So that means force is stiffness. That's why we call it stiffness. So stiffness 1. So we only have one value, right? So stiffness 1 is going to be this bending moment, right? Because we are considering the force. So the force corresponds to that rotation is a bending moment, right? So this is in clockwise direction. This is also in clockwise direction. So the total bending moment is going to be, so we are considering total bending moment. Okay, you remember? Total bending moment is going to be 4EI over L plus 8EI over L. So that's going to be 12EI over L, right? So the action unit, that's going to be, the first one is this reaction, right? I don't remember first thing is not bending moment. So bending moment is 2EI over L. So the reaction is 6EI over L squared. That's in negative direction because we took upward positive. So everything is according to our sign convention, right? Why this is negative? Because we choose upward positive. This force is originally in the downward direction, right? So VB is going to be 6 EI over L minus 12 EI over L. So that means downwards 6 EI over L. Right. So this is going to be 12 EI. So the reaction and bending moment is clockwise direction for EI over L. Right. So now I need to consider the displacement equation. So I know my force plus stiffness into displacement, right? So I know we are considering the equilibrium. Why? That is what we are taking as the core in displacement method, equilibrium and force method compatibility shape. So the equilibrium at joint B is, we know, the theta and the corresponding force is MB, right? We know the total bending moment is 0, right? So it's in equilibrium, so the total bending moment is going to be 0. Actually, for this case, it is 0. And for the primary structure, we got minus WL over 24, right? We only have one stiffness coefficient because we don't need matrix then. 12 EI over L. So this is the force. So we make it 0 and then we separately apply a unit rotation to B joint and calculate the force. Okay. So the actual force is, we need to multiply it by MB, right? Because this is for a unit, sorry, theta B, because this is what we need to find, right? This is what we need to find, right? We apply a unit theta, so theta is equal to 1, and if this is for a unit rotation, what will this value be for the actual rotation, right? So if I, so 12 I over L into theta B, right? So I don't need any matrix because this linear equation, right? So yes, I can go ahead and find it. So when I plug these two equations, so when I sum these two systems, right? So that will have theta, that will have no theta because we set it 0, and you should get the final structure, right? So we are not considering any displacement directly, but we are solving for the equilibrium and the equilibrium, right? This is a force, right? Force per unit displacement and multiply it by the original displacement. This is also a force, right? And we solve for displacement. That's what we are doing in displacement method, right? This is a force, this is a force, this is a unit force multiplied by the displacement. Again, we are getting a force, right? So we consider equilibrium. So if you plug these values, right? So your displacement will be WL over 24 is equal to 12 EI over L theta B. So your theta B is going to, theta B is 12 into 24 means how much? 288. Yes, 288. W L squared over I. This is positive, so that means theta b is in clockwise direction, right? Theta b is in clockwise direction, right? Theta b, and we can find the actions as well. So the actions is equal to actions in the restraint structure, right? So these are the action for a unit displacement, and then you need to multiply it by the original displacement, right? So we are actually doing superimposing, right? That's it. We are doing all this time. Why we are separating to something we superimpose? Because it's easy to analyze when things are simplified. That's we are doing when we separating, right? We separate the load with zero displacement, right? We just apply a displacement to separate structure, right? That's what we are doing. We keep everything simple, right? And yes, we can multiply AU to D, right? So the displacement for a unit force. So this is a force. This is a force in the primary structure. This is unit force. This is the displacement. And this is giving a force, right? So you can write WL over 2L. So I can take WL over 24 out, right? Here as well. No, I will keep it here. WL over 12, W over 2. W over 2. And this is going to be WL over 8. We substitute QL as W, right? That's why we got easy to simplify. Else it's bit difficult, right? Q and W terms, right? So this is going to be 2EI over L. 6EI over L squared, 6EI over L squared, right? To LEI over L squared. Or EI over L. Is going to be multiplied by WL cube over 288 EI. WL squared, right? WL squared over. So you can see EI is going to be cancelled with each term. when you multiply it by this, right? Okay, so you can write this part. How it's going to be WL squared over, sorry, WL over 144. Is that right? 2WL, yes. So this is going to be so this is going to be minus W over 48, right? When you multiply this by this, L squared getting cancelled, W over 48, right? Yes, this is also. And this is going to be twice of that, right? So that's going to be W over 24. And this is going to be twice of this, WL over 72, right? So you need to add these to this matrix, right? So once you add it, so your final values going to be this is MA, this is VA, this is VB, this is VC, and this is MC. And this is going to be 48, 48, so it's 48 over 4. So that's going to be minus 5 WL over 48. W over 2, W over, what is this? Did I make a mistake? Yes, right. This is going to be, sorry. This is not. We should add these two. So when you add it, it's, you can multiply both by 2L and 2L. So that's going to be 144 and 2L. So that's going to be minus 2L and plus 1. So that's going to be negative 11. Oh. So then you need to add these two. So this is going to be 4. If you multiply by 24, 24, both 24 W over 48, right? 24 minus 1. So that's going to be 23, right? So this is going to be 48, 48. So this is actually 48 W over 48, right? So 48 minus W means 47, right? Right. So this is going to be plus. This is 24W, sorry, you can multiply by 2L and 2L. So because to get the same denominator, right? 24, 12 plus 1 is 13. So here you have WL over 8. So to make the same denominator, I will multiply it by 9. This is what I did in each step, right? 9 WL over 72 WL over 72. So that's going to be 10 WL over 72. And I can write as 5 WL over 36. So you can see actually this value is anti-clockwise, right? So this is actually in this direction, anti-clockwise. This is positive, so that means it's in upward direction. This is positive, it's in upward direction. This is positive, it's in upward direction. This is positive, so that's in clockwise direction. So that's how we can simply solve this, right? So this is pretty simple way, right? So you can determine, you can try this example, right? Try this. And take the same assumption, W is equal to QL when you simplify, right? This has no loading. And here you have two unknown displacement, theta B and theta C. So reference A, B, C, D. And you will have two displacements, right? So you need to do it in each step, right? So that means you need 2 by 2 matrix. When you are solving this, when you are solving this equation, you will have 2 by 2. Okay. So try this one, right? You can solve for each reaction. So no need of, there will not be horizontal reactions, right? So bending moment, vertical reaction, vertical reaction, vertical reaction. This is not symmetric also. Vertical reaction and the bending moment. You can solve for these actions. You can solve for these actions. So there will be altogether 6 actions, right? So try this example, okay, using displacement method. Right. Thank you. So when you add displacement like this, so you have to add each at a time, right? So if you're adding, so this is your primary structure, you fix everything with loading, and then secondly you will be applying a unit displacement to this location, right? And third, you apply a unit displacement to this location. Okay, so once you add all of these three, you will get the final structure, right? Thank you.